Hello everyone, this is the second lecture on the synchronous sequential logic. Today we will cover the design part of it. If you remember from our previous class, the analysis of sequential circuits commences from a given circuit diagram and culminates in state equations, state table, and finally a state diagram. The design of sequential circuits start with a set of specifications. This was also the primary step in combinational circuit design. Then the procedure continues with drawing the corresponding logic diagram. It's important to obtain the correct state diagram that addresses a certain requirement of the specification. It may happen that two circuits having two different states in their state diagram, and yet they perform the exact same functionality. Therefore, it is sometimes important to reduce the number of states in the state diagram if it's ever possible. This will also reduce the number of flip-flops in the design. So I first start with state reduction techniques, then move on to the state assignment problem and talk about the trade-offs associated in each of these design steps. State reduction problem deals with reducing the number of states in a given state diagram while keeping the input-output relationship unchanged. To be able to understand how a state reduction algorithm works, it is best to review an example. This state diagram shown in this slide is a directed graph showing the relationship between the states of the system. Let us assume we have 6 states labeled using the first 6 letters of the alphabet, A, B, C, D, E, and F. The arrows show the transitions from each state based on the provided input and the resultant output bits, so that there are 2 outgoing arrows for each state, one for the input 0 and the other for input 1. You can realize that the graph is connected and you can traverse all the states provided that the appropriate input is fed into the circuit. The state diagram may seem a bit complicated, but we will see that this state diagram can be simplified without changing the input and output relationship. Let us observe the state table that can be derived from the state diagram. If we inspect the state table closely, we realize that C and D states have the exact same state changes on a given input bit. They also produce the same output for the same input. This means that these states are interchangeable and represents the same state, and therefore one of them can be eliminated. After elimination of, let's say state D, then we'd replace all D's in the table with C, since states C and D are equivalent. Next, we inspect for any other state that can be eliminated in the reduced state table. We figured that state B and F generate the exact same states and output values for both input x0 and x1. Therefore, we eliminate state F and replace all F's in the table with state B. Finally, we reach to the 4-state state diagram whose state table is shown to the right of this slide. As can be observed, there are no redundant states at this reduction stage, so we stop. If we draw the simplified state diagram, we obtain the diagram drawn to the left of this slide. As you can see, the state diagram is dramatically reduced to a much simpler form. It is easier to work with this state diagram when we design the synchronous sequential logic. Next, we explore the state assignment problem. In order to design a sequential circuit, it is necessary to assign unique coded binary values to the states. Let us say we want to design a sequential circuit, and after we reduce the number of states to m, we need to code each state using n bits, where n is greater than or equal to log m in base 2. If we consider our previous state diagram, we could have 2 different state assignments as shown in tables at the bottom. The first code uses 2 bits to represent each state, which is the most straightforward state assignment methodology. And the second code uses 3 bits to represent each state. Although 2 bits are enough to represent, 3 bits might be useful because 4 code words are assigned to the states, and the remaining other 4 code words, remember there are 8 possibilities with 3 bits, will just be don't cares. And we already know that don't cares can help simplify the combinational logic. Although it's not certain, the second code assignment may end up in less combinational logic around the sequential logic when we perform our design. We could alternatively have used gray coding or one-hot coding and other coding techniques. Please search such coding options on web and learn about pros and cons of each scheme and their relationship with our discussion on sequential circuit design. After the assignment process, each letter is replaced by the corresponding code in the state diagram as shown to the left of this slide. Finally, I'd like to touch on one more important table that should be useful in designing sequential circuits. That's called excitation tables. The design using JK and T flip-flops is complicated due to the inputs must be derived from the state table. In case of D flip-flop, input equations to the flip-flop can easily be obtained directly from the next state because D flip-flop at clock transitions enables the output to be equal to the input value. In other words, the next state to be equal to the input value. It's not the case for JK and T flip-flops. To derive the input equations, we need the functional relationship between the state table and the input equations. This functional relationship is illustrated usually with something called excitation table of the flip-flop. The excitation table for D flip-flops is simple because the next state depends only on the input, nothing else. This operation with D flip-flops make the sequential logic circuit design simpler compared to the designs with JK and T flip-flop. However, JK and T flip-flops provide more freedom and we can end up with less combinational logic added to our sequential circuit design using this freedom. Plus, most of the time JK and T flip-flops are cheaper compared to D flip-flops. We'll see an example to support these arguments and the comments next by walking through a real design example. Let us summarize the design procedure in this slide. To my count of the operation, there are basically 7 steps to go through when we design a sequential circuit. To some designers, some of the steps could be merged. I won't object to that. First step is to understand what the circuit specification is. This could be your boss telling you what you need to implement. In other words, we read the word description that's provided to us to learn what we are supposed to design. Next, we reduce the number of states if we need to, using state reduction techniques. If we draw the state diagram wisely, most of the time we may simply skip this step because it will no longer be needed. But for complicated designs, this step can be a lifesaver. Thirdly, we assign binary values to the states of the system. We later obtain the state table where states are represented by binary codes. Next, we choose the type of the flip-flop we would like to use in our design. Since each flip-flop have different functional relationship between the state table and the inputs, we use excitation tables to derive the input and output equations based on the choice of the flip-flop. We simplify the combinational logic using Carnot maps and finally draw the logic diagram. To see these design steps in action, let us consider an example. Let us have a specification that we need to detect a sequence of 3 or more consecutive zeros for a given binary bit stream. This is usually a required application for most recording devices in which long runs of zeros cause signal levels stay low for a long time and timing recovery circuits do not function properly if the signal level stays low for more than a period of time. Therefore, such systems employ run length limited codes to break long lengths of both zeros and ones even though the input data stream have those longs and runs of zeros, encoded stream do not have it. Our circuit is aimed at finding such stream of bits in which there is one or more than one run of 3 or more consecutive zeros. After giving you a brief insight about why runs of zeros and ones might be important, let us proceed with the corresponding state diagram. Our system begins with the reset state as 0, where we assume the input bits start streaming. As long as the incoming bits are 1, we stay at the same state until a 0 bit carries us to the next state as 1. If the next bit after 0 is 1, we go back to initial state as 0. If, however, we have another 0 and another 0 after then, we will end up in state as 3, where we give an output of 1, meaning that we found 3 consecutive zeros. If more than 3 zeros occur in order and sequentially, we will stay in state as 0 indefinitely until 1 is seen in the input stream, and we transition the state to S0 again. Note that the state diagram cannot be simplified, so we skip the state reduction step. We will use simple state assignment and binary codes to represent states. After determining the state diagram, next stage is the state table. As can be seen from the state table, drawn to the left of this slide states S0 is assigned 0, 0, S1 is assigned 0, 1, S2 is assigned 1, 0, and S3 is assigned 1, 1 binary codes. Based on the binary coded state diagram, we can easily generate the state diagram as shown to the left of the table. Since the excitation table for D flip-flop is simply the equality between the input and outputs, the next state values in the state table specify the D flip-flop input conditions. Using kernel maps and function simplification techniques we previously covered, we can obtain the flip-flop input state equations as shown. AT plus 1 equals AX prime plus BX prime, BT plus 1 equals B prime X prime and AX prime, and Y, the output, equals AX prime. I avoid using AT and BT to simplify the notation. By completeness, you can include them in your expressions. Please verify that they are correct by drawing the kernel maps and finding essential prime implicants. Finally, we draw the logic diagram of the circuit. The key idea here is to derive the state equations correctly. The rest is just wiring up the circuit using the appropriate inputs and outputs and ports. Note that both flip-flops are clocked synchronously and there are no gates affecting the clock signals. This is quite essential when we design synchronous logic circuits because gating this clock signal may lead to asynchronous operation. This discussion will be revisited again when we discuss registers and counters in the next lecture. The design with JK flip-flops follow the same steps, except we need to use excitation tables to derive the input conditions for the J and K input terminals of the flip-flop. Let us use 2 flip-flops for our design. You could use more flip-flops, by the way. It will increase the number of states in our system, although a subset of them would not be used. I recommend trying 3 flip-flop design yourself to get a bit feel of what's going on. The JA and KA are the inputs of the first flip-flop that we name A. The JB and KB inputs are for the second flip-flop that we name B. Based on the excitation tables, we find the appropriate zeros and ones and don't care conditions for JA, KA, KB, and JB ports. For example, AT and AT plus 1 being 0, 0. We need JA and KA to be 0 and don't care respectively. And for BT and BT plus 1 to be 0, 1, we need JB and KB 1 and don't cares respectively to be 1 and don't cares respectively, and to be able to satisfy the state transition of 0, 0 and 0 to 0, 1. This relationship is shown with the blue arrow in the first row of the state table. You can follow the same procedure to find out the other input conditions for both of the flip-flops by running through the rows of the state table. Next, I will show the corresponding 4 kernel maps for 4 inputs of the JK flip-flops. If we draw the corresponding kernel maps for each input, we can calculate the state equations for each input of the JK flip-flops as shown. The circuit optimization techniques we learned earlier are useful here, while we're trying to minimize the combinational logic connected to the flip-flops in order to meet the detection of zero-round specification. After finding out the J and K inputs of flip-flops in terms of state variables and inputs, like X, the output Y does not change in the JK implementation, and it's still AX prime, by the way. So using the flip-flop input state equations as well as the state equation for Y, we finally obtain, the logic diagram, and that's how we draw it. You can immediately realize that for the implementation of the same objective, this design based on JK flip-flops used less number of logic gates. In other words, less complex combinational circuit around the sequential logic circuit components. This way, using flip-flops other than D-type can help us solve various trade-offs associated with the complexity of the digital design circuit and its manufacturing process. I'll leave the design with T flip-flops as an in-class exercise and leave you to decide on the best design by comparing all the designs using 3 types of flip-flops. In this class, we covered the design procedures for synchronous sequential logic circuits. Coming up with the best design is usually attained through long years of experience. Yet we have shown the basic design methodology one needs to follow to be able to meet the design specifications. After covering 2 complete classes on sequential circuits, in the next lecture we will learn more about the fancy logic components of digital systems, particularly sequential ones, such as registers and counters. You will see a variety of different sorts of designs that serves a set of particular purposes and enrich our understanding of sequential logic idea. Please feel free to drop any questions you might have about today's lecture or previous lectures into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.